So in this hypothesis test, an engineer wants to know if producing metal bars using a new treatment rather than the conventional treatment makes a difference in the strength of the bars. So this is a common way where you would want to use a hypothesis test. We introduce something new and we want to see if it's actually different than our old method of doing things. So we have actually a table of data here, a sample using the experimental method, and then a sample using the conventional method. So first, let's start off just identifying our null and our alternative. So we're trying to see if there's any difference here between the two methods. So that's our claim, is that the new treatment makes a difference. So our null needs to be that the two population means are the same, there is no difference, and that lets us have our alternative hypothesis that there is a difference. The means are not equal to each other from the two populations. And now if we can run a hypothesis test, if we're able to reject the null, then we have reason to believe the alternative is true and we can accept our claim and prove that our claim is true. So our claim is the alternative. So first let's find the critical values. And that's all based off of our alpha here in our rejection region. So coming into Excel, if you look right here, let me zoom in, I guess, a little bit. Our degrees of freedom, it's going to be 15 in this case. We had from the problem that we are assuming the population variances are equal. And so we know we're in this situation. We're testing two samples. We're using the t-test because we don't know the population variances, but if we assume those are equal, our degrees of freedom is to add the two sample sizes together and subtract 2. So this is when the variances are assumed to be equal from the two populations. And so that's what we're doing, add our two sample sizes together, and we're going to get 17, subtract 2 is 15. So use our formula here. For a two-tailed test, we can just use this one here. We have a two-tailed test because we're just using not equal to as our alternative. So we put in our alpha, which is 0.10. Our degrees of freedom is 15. And it gives us the critical value. So it gives us the positive version, two-tailed. By the symmetry of the t-distribution, we know that just that negative version, or put a negative in front of that number, would be the left-hand critical value. So if we get a test statistic back that's outside of this range, that means it's really far into the tails, we will reject our null hypothesis. And that's what this is saying right here. If our test statistic is less than that negative value, or if it's greater than that positive, we're going to reject the null hypothesis. That's our rejection region. So how do we find the test statistic? So let me again go back. This is on page 428 of the text. We're assuming the variances are equal, so we're going to need to calculate this right here. So the first thing to do is calculate this, which has the long formula right here, and then we're going to multiply it by the square root of 1 divided by the first sample size plus 1 divided by the second sample size. So I break that up into steps here in Excel here. So you need to find the actual standard deviations. So you need to copy over, and you can click here and copy or open in Excel. But then in Excel, you can just use the formula to find the means. You can use average and select the data, and then you can use standard deviation.s for sample and select the data. And you do that for each of your two samples, and you'll get the mean of each sample and the standard deviation of each sample. So then you can use that formula I just showed in the book. You're going to take 1 minus that first sample size and multiply it by that sample standard deviation squared, and then add that to 1 minus the second sample size times that second sample standard deviation again squared. And that's the top part of the fraction, and on bottom you're dividing by that degrees of freedom, the two samples added together, and subtract 2. So 17 minus 2 is 15. So the top part of the fraction, the bottom part, and you take the square root of that whole thing. And that is this right here. And so then when we're going to multiply it by that next square root, which is this number, 1 divided by the first sample size plus 1 divided by the second sample size, the square root of that sum. And then you have those two numbers that you're multiplying together, and that gives you the standard error that you want. And so that's what I'm doing here, just multiplying those two results together. And so then finally, to get the test statistic for our particular samples here, we take the mean of each sample, subtract sample 1 minus sample 2, and divide by that standard error. And that gives us our test statistic, which 0.63 is not outside the range of our critical values. It has a smaller absolute value. It's closer to 0, closer to the center of the distribution. So it's not in the rejection region, which means we will fail to reject the null hypothesis. Which just in terms of what this problem's all about is there's not enough evidence to support the claim that this new method of producing metal bars changes the strength of the bars.